When a user's finger touches the glass of a smartphone, the device has just a few milliseconds to process that physical contact and draw an entirely new image on the screen. Delivering that instantaneous response relies on a specific structural component of the Android operating system, the main thread, also known as the UI thread. The main thread carries a dual responsibility. It is the only pathway allowed to receive inbound interaction events from the user, and it is the only pathway authorized to push outbound rendering commands to the display. Modern mobile applications are data-heavy. They parse massive JSON payloads, decode high-resolution imagery, and query local databases. Yet all of that resulting interface data must ultimately pass through this one specific pipeline. This creates the primary constraint of the Android architecture. Resource-intensive workloads must be kept off the main thread. There are 4 primary categories of heavy workloads that frequently challenge this constraint: local database access, external network requests, large file loading, and complex image processing. A smooth user experience requires a consistent 60 frames per second. But when these heavy blocks attempt to move through the central node, the thread begins to stall. To the user, the symptoms of this overload are immediate. Scrolling becomes laggy, animations stutter, or the entire screen freezes. To fix this, we must look at the mechanics. Why does fetching database rows physically stop the processor from drawing pixels? The answer lies in the strict temporal mathematics governing how the main thread operates under the hood. The main thread functions as a sequential event loop, a specific type of queue where tasks are executed one at a time, in the order they arrive. This horizontal timeline represents the main thread schedule. To maintain 60 frames per second, the thread must calculate and dispatch a new frame exactly every 16.6 milliseconds. That is a hard deadline. Standard, lightweight touch events enter this queue and are processed quickly, taking up only a fraction of that 16.6 millisecond window. The rendering commands immediately follow the touch logic, assembling the visual layout and also completing well within the same time boundary. Because the math finishes before the deadline, the completed frame is dispatched to the physical display exactly on time. The defining characteristic of this event loop is its sequential execution. It operates in single file. No subsequent operation can begin until the current operation in the queue has entirely finished its run. This sequential nature makes the entire rendering engine highly vulnerable. A single task that overstays its 16.6 millisecond welcome will stall every frame behind it. The first major threat to this sequence comes from I/O-bound operations. These are tasks that rely on external input and output, primarily local database queries, large network requests, and loading files from a disk. When a massive network request drops into the queue, the processor isn't actually calculating. Instead, it is forced to sit idle while waiting for a remote server and network latency to respond. This waiting period instantly violates the 16.6 millisecond rendering deadline. Because the thread is blocked waiting for the network payload, the scheduled rendering commands trapped behind it are skipped entirely. In the user's hands, these dropped frames manifest as UI lag and scrolling stutter. The application lags not because the device processor is overworked, but because it is trapped doing nothing. I/O operations starve the rendering queue of time, breaking the illusion of a responsive interface. The second category of system threats comes from CPU-bound operations. Image processing is the primary example, requiring intense pixel-by-pixel mathematical calculations. Look at the CPU utilization graph above the timeline. During image processing, the thread is not waiting for a server. It is utilizing 100% of its available processing cycle. This causes a distinct failure. While the processor grinds through the image data, inbound user input events, like taps or swipes, cannot enter the active timeline. The thread is too consumed with calculation to acknowledge that a user is touching the screen. If those input events remain blocked in the buffer for longer than 5 seconds, the Android OS flags the application. This triggers an application not responding, or ANR, error. The OS freezes the app and prompts the user to force close. Whether the thread is idling for external latency or monopolizing compute cycles for math, placing heavy tasks on the main thread leads to systemic failure. Solving this requires a specific architectural separation, execution segregation. To protect the 16.6 millisecond rendering loop, heavy tasks are routed away from the main thread entirely and moved to a parallel background pool. High-latency database queries and high-compute image operations are assigned to these secondary threads. This segregation immediately frees the main thread. It can continue processing user inputs and rendering intermediate states, like loading animations, without interruption. This creates a new challenge. Once the background thread finishes its work, it must send the finished data back to the UI. Android uses callback or message passing mechanisms to bridge these two threads. The background thread delivers a message that slots into the main thread's queue, triggering a fast final rendering pass to display the result. Implementing concurrency is not just about executing tasks faster. It is a defensive mechanism to protect the integrity of the UI event loop. Remember, do not block the UI thread. This is a hard constraint dictated by the sequential mathematics of Android's event loop. Maintaining performance requires actively isolating specific threats from this loop, beginning with latency traps. Database access, network requests, and large file loads will force the processor into an idle wait state, starving the queue of time. Meanwhile, computational threats like image processing will monopolize the queue, blocking out user input entirely. Apps that violate these rules become laggy and prone to ANR errors. Apps that adhere to them maintain a fluid, responsive 60 frames per second. Knowing how to effectively identify these workloads and route them to background threads is the primary differentiator between an average developer and a senior architect. Mastering the main thread ultimately means knowing exactly what workloads must never touch it.